This is a PowerPoint for Chapter 8 entitled Wind and Weather for the AMS Weather Studies course at Mohawk Valley Community College, WE 101. Wind is the principal focus of this PowerPoint, and wind is the local motion of air measured relative to the Earth's surface. The chapter that we're going to look at covers the various forces that initiate or modify this atmospheric circulation, and we're going to look at each one of these multiple forces individually to give you some idea how they bring about this thing called wind. We're also going to talk a little bit about monitoring wind speed and direction, and talk about scales of atmospheric circulation at the end of the PowerPoint. As we'll see, several forces influence wind direction and speed. A force is defined as a push or pull that can cause an object at rest to move, or that alters the movement of the object already in motion. Like the wind, a force has both direction and magnitude and is considered a vector quantity. Forces acting on the wind are things listed on this slide, such as air pressure gradient, centripetal force, Coriolis effect, friction, and gravity. And we're going to talk about each of these individually throughout this presentation. In examining the various forces that govern the wind, it's useful to apply each force to a parcel that is a unit mass, for instance, a kilogram of air. Imagine that the wind is nothing more than a continuous stream of air consisting of discrete air particles. And we can assume that any force acting on an air parcel has the same influence on the stream of air parcels, in other words, something we call the wind. In describing each force that affects air motion, we can examine the force per unit mass of air. In meteorology, force and acceleration are terms that are often used interchangeably because it is common to treat forces as acting on a unit mass of air. Let's start with one of the forces that govern the wind, and this is called the pressure gradient force. A gradient is simply a change in some property over a distance. An air pressure gradient exists whenever air pressure varies from one place to another, between locations. As we saw earlier, spatial variations in air pressure can arise from contrast in temperature, differences in water vapor concentration, or both. In addition, winds diverging or converging over broad regions can bring about air pressure changes by redistributing the amount of air in a vertical column of the atmosphere and inducing air pressure gradients. Now, air pressure gradients can occur both horizontally and vertically within the atmosphere. A horizontal pressure gradient refers to air pressure changes along the surface of a constant altitude, such as mean sea level. As the slide points out, a vertical pressure gradient refers to the air pressure change directly above the Earth's surface, and this is a permanent feature of the atmosphere. Air pressure is determined by the weight of the overlying air, so air pressure is greatest at the Earth's surface and always decreases with altitude. We're very familiar with the idea of isobars. We've used them in our labs, and these horizontal air pressure gradients can be determined on weather maps from patterns of isobars joining lines that have the same air pressure. As we know, when we look at maps, the horizontal air pressure gradient is relatively steep, as we see in example A, where isobars are closely spaced, and weaker, as we see in the diagram below, where isobars are farther apart. It's important to note that air pressure gradients are always measured in the direction of greatest change, that is, perpendicular to the isobars. So the question we might ask is, how do air pressure gradients influence the motion of air? Consider this situation. Suppose the bathtub is partially filled with water. as we see in this particular figure. Sloshing the water back and forth from one end of the tub to the other creates rapidly changing pressure gradients at the bottom of the tub. Most of the time the water surface is not horizontal. The water pressure acting on the bottom is high where the water is relatively deep, or lower at where the water is relatively shallow. If we stop agitating the water, the sloshing back and forth then dampens and the undulating surface returns to horizontal. The water pressure along the bottom is then the same from one end of the tub to the other. Thus, in response to the water pressure gradient, water flows from one end of the tub, where the bottom water pressure is greater, to the other end, where the water pressure is less, thereby acting to eliminate the pressure gradient. Similarly, when a horizontal air pressure gradient develops, air flows in the direction to eliminate the pressure gradient. The force that causes air parcels to move as the consequence of an air pressure gradient is known as the pressure gradient force, and always directly reacts perpendicularly to isobars and towards the lowest pressure. Another force governing the wind is known as centripetal force. Isobars, we know when they're plotted on the surface weather map, are always curved, or most of the time they are. This indicates that there is a pressure change, or a pressure gradient force change, direction from one place to another. Consequently, horizontal wind blows generally in a curved path, and this curved motion indicates the influence of something known as centripetal force. Centripetal force is easily demonstrated, and this diagram demonstrates that. A rock is tied to a string and then whirled about so that the tethered rock travels in a circular orbit of constant radius. The string exerts an inward force on the rock, confining it to the curved, or what we know as circular, path. From the diagram you can see that the direction and motion of the rock is related to the center force, or centripetal force, or center-seeking force. If we were to cut the string, the centripetal force no longer operates and no longer confines the rock to a curved path. The rock would obviously fly off into a straight line, described by Newton's first law. That is, an object in a straight line, unaccelerated motion remains that way unless acted on by an unbalanced force. A centripetal force then operates whenever air parcels follow a curved path. As we will see later, centripetal forces arise from imbalances and other forces operating in the atmosphere. It is not a direct force itself. The next force we're going to talk about is the Coriolis effect, or Coriolis force. The rotation of the Earth creates another force, which we call the Coriolis force, and this particular force acts upon wind and other objects in motion in very predictable ways. If we go back to Newton's first law of motion, we can assume that air will remain moving in a straight line unless it is influenced by some sort of unbalancing force. The consequence of the Coriolis force opposes pressure gradient acceleration in that the moving air changes direction. Instead of wind blowing directly from a high to a low pressure, the rotation of the Earth causes wind to be deflected off course. In the northern hemisphere, wind is deflected to the right of its path, while in the southern hemisphere it's deflected to the left. The magnitude of the Coriolis force varies with velocity and latitude of the object, and we'll see this in the next slide. Coriolis force is absent at the equator and its strength increases as one approaches either pole. Furthermore, an increase in the wind speed also results in a stronger Coriolis force, and thus in greater deflection of the wind. Coriolis force only acts on air when it has been sent into motion by the pressure gradient force. And most importantly, we should appreciate that the Coriolis force only influences the wind direction and never the wind speed. This slide shows how the Coriolis force is latitude dependent, that is, at 0 degrees at the equator there is very little force, and as we go up in latitude we find that the Coriolis force is much greater. As an example, let's say we wanted to throw a baseball from the center of the country, say in Omaha, Nebraska, and we wanted to send that baseball, if we had a strong enough arm, to maybe Washington, D.C. Well, if the Earth were not rotating, we could, with a strong enough arm, take and throw a baseball from here to here with no problem. However, because of the rotating Earth and the axis on which the Earth rotates, we find that if we tried to throw a ball from Omaha to Washington, it would end up somewhere in North Carolina because of the Coriolis effect, or the movement of the object to its right in the northern hemisphere. This diagram shows that large-scale winds are deflected to the right of their initial direction in the northern hemisphere and to the left of their initial direction in the southern hemisphere. And this deflection, which is known as the Coriolis effect, is maximum at the poles and 0 at the equator. We should notice also that the slide points out that faster moving objects deflected more than slower because of faster objects cover greater distances. The longer the trajectory, the greater the shift of the rotating coordinating system, and in reality, Coriolis effect only significantly winds that are in very large scale weather systems. So local winds generally are not affected by the Coriolis effect. Another force governing the wind is something called friction, and we're all familiar with friction as the resistance that an object or medium encounters as it moves in contact with another medium. And we are all familiar with that relative to heavy appliances moving across the floor or trying to pull something that has a lot of friction associated with it. Friction not only affects heavy objects, but the friction also affects fluids, both liquids and gases. The friction of fluid flow, which is known as viscosity, is of two types: molecular viscosity and eddy viscosity. And eddy viscosity is extremely important when we talk about wind and weather. Rocks shown in this riverbed are obstacles that break the current, which may be very rapid, into turbulent eddies downstream from that particular flow. This will slow down the river at this point, or stream, and we can basically equate that to, say, frictional interaction that takes place with wind. If wind encounters obstacles on the Earth's surface, it also will have an effect on its speed and maybe even direction. This picture of a snow fence also provides a practical illustration of the frictional slowing of the wind. A snow fence slows the wind, reducing its ability to transport snow in suspension. Hence, snow accumulates immediately downwind from the snow fence. The fence traps some of the wind's kinetic energy by breaking the wind into things called eddies, which we've talked about, and the wind diminishes, speed diminishes, losing some of its snow transporting ability. And that's why the snow accumulates on the downwind side of the fence that we see in this illustration. One of the things we know about forces that govern the wind is a force called gravity. Gravity always acts directly downward. Because of this, gravity, unlike the Coriolis and friction forces that we talked about earlier, gravity does not modify the horizontal wind. Gravity influences air that is ascending or descending, such as updrafts and downdrafts, and gravity is responsible for the downhill drainage of cold, dense air. Air parcels, like all other objects with mass, are subject to the force of gravity, which pulls these air parcels to the Earth. If we did not have this gravity, the air parcels would leave the Earth and we'd have a lot of trouble breathing. This next slide shows a summary of the forces that we've just talked about. So you should look these over and go to your text in Chapter 8 and look these over, especially the summary section, which will kind of put all of these things together for you. So, to this point, we have examined forces operating in the atmosphere as if each one of the forces acted alone, independent of all the others. In reality, these forces obviously interact and govern both wind speed and direction. In some cases, two or more forces achieve a balance or equilibrium. From Newton's first law of motion, when forces acting on an air parcel are balanced, the parcel either remains stationary or continues to move along a straight path at a constant speed. When forces are balanced, the net acceleration is zero. In this next series of slides, we will build an increasingly sophisticated model of atmospheric motion by examining how forces interact in the atmosphere to control the vertical and horizontal motion of the air, that is, the wind. The interactions result in hydrostatic equilibrium, something called the geostrophic wind, the gradient wind, and surface winds, that is, horizontal winds within the atmospheric boundary layer. In developing a realistic model of the atmosphere, as far as the motion is concerned, we will assume that the atmosphere is in a state of hydrostatic equilibrium. This assumption allows us to focus on horizontal motion of the air. We know that air pressure decreases with increasing altitude, so that a vertical air pressure gradient is a permanent feature of the atmosphere. This schematic diagram shows that forces are basically equal, where the pressure gradient is directed upward from higher air pressures to the Earth's surface towards lower air pressures aloft. If this force acted alone, the vertical pressure gradient force would accelerate air away from the Earth, and we would be left without an atmosphere. So the vertical pressure gradient force is almost balanced by the equal but oppositely directed force of gravity. The actual balance of these two forces is called the hydrostatic equilibrium. The geostrophic wind model is an unaccelerated horizontal movement of air that follows a straight path at altitudes above the atmospheric boundary layer. It results from a balance between the horizontal air pressure gradient force and the Coriolis effect. The Coriolis effect is significant only, again, in broad-scale circulation, so that the geostrophic wind develops only in large-scale weather systems. This diagram approximates the evolution of the geostrophic equilibrium, a balance between the horizontal pressure gradient force and the Coriolis effect. The geostrophic wind blows parallel to straight isobars at altitudes above the atmospheric boundary layer. An air parcel initially at rest will move from high pressure to low pressure because of something known as the PGF, pressure gradient force. However, as the air parcel begins to move, it is deflected by the Coriolis force, or the Coriolis effect, to the right in the northern hemisphere, or left in the southern, as we've discussed. As the wind gains speed, the deflection increases until the Coriolis force equals the pressure gradient force. At this point, the wind will be blowing parallel to the isobars. When this happens, the wind is referred to as geostrophic. A more common model of the atmospheric flow is known as the gradient wind, that shares many of the same characteristics as a geostrophic wind. It's a large-scale horizontal and frictionless model and blows parallel to isobars. However, the most important distinction between the two models is that the geostrophic wind blows in a straight path, whereas the path of the gradient wind is curved. Gradient winds develop at altitudes above the atmospheric boundary layer around a dome of high air pressure, that is, an anticyclone, or a low pressure called the cyclone. This diagram shows the balance of forces that create the gradient wind in the northern hemisphere. PGF is the pressure gradient force. The CF is the Coriolis effect. The CE is a centripetal force. And in this diagram, we can see how these forces affect the rotation of the wind around a low versus around the high. And this is why the counterclockwise-clockwise situation occurs in the lows and highs that we're familiar with. Similar diagram in your PowerPoint shows that viewed from above in the northern hemisphere, the gradient wind blows clockwise and parallel to isobars in the anticyclone, and the gradient wind blows counterclockwise and parallel to isobars in a cyclone. Geostrophic winds and gradient winds are frictionless. That is, they occur at altitudes where friction is limited. How does friction affect horizontal winds within the atmospheric boundary? We should appreciate that friction should slow down the wind, but in addition, friction will have other forces that are interacting and alter wind direction. As we can see in this particular diagram, within the atmospheric boundary layer, friction slows the wind and shifts the wind across isobars towards the low pressure, as we can see here, due to this force of friction. We can say therefore that horizontal winds strengthen with altitude throughout the atmospheric boundary layer. Furthermore, the angle between wind direction and isobars is greatest near the Earth's surface, but decreases with altitude and is essentially zero at the top of the atmospheric boundary layer. This can be seen in this particular figure. Above the atmospheric boundary layer, the horizontal wind is either geostrophic, where isobars are straight, or gradient, where isobars may be curved. The patterns of surface winds associated with a cyclone is the basis for a simple rule of thumb for locating the center of a cyclone. In a northern hemisphere location, if you stand with your back to the wind and then turn approximately 45 degrees to your right, the cyclone center will be located to your left. On a typical surface weather map, isobars exhibit anticyclonic curvatures, which are called ridges, and cyclonic curvatures, which are called troughs. And there is an example of both of them. Troughs generally bring in cooler, cloudier weather. Ridges tend to bring in warmer, drier weather as they approach. Like all fluids, air is continuous, and this continuity implies a link between the horizontal and vertical components of the wind. For example, surface winds are forced to follow Earth's undulating topography, going up hills, descending into valleys, and in addition, uplift occurs along frontal boundaries as one air mass advances and either overrides or pushes under another retreating air mass. In this idealized vertical cross-section of an anticyclone, horizontal winds converge aloft, air descends, and surface winds tend to diverge. In another idealized look at a vertical cross-section of a cyclone, surface winds converge, air ascends, and winds aloft diverge. This figure shows that when surface winds accelerate and undergo horizontal divergence as they blow from a rough to a smooth surface, that is from, say, land to water, surface winds slow and undergo horizontal convergence when blowing from a smooth to a rough surface, that is from water to land. Divergence of surface winds causes air to descend, whereas convergence of surface winds causes air to ascend. This slide talks a little bit about wind velocity, wind direction, and some of the instruments which measure the horizontal wind. This is a Beaufort scale, which is the scale that's associated with wind force, ranging anywhere from 1 to 5 knots per hour, which is equivalent to about somewhere around 3 miles an hour, upwards of 39 to 49 if we talk about a strong breeze, that's 30 miles an hour or so, all the way up to a hurricane, which is 119 and over, which in miles per hour is about 74 miles per hour. So anything over 74 miles per hour in terms of wind force is considered a hurricane. This slide talks about some of the common instruments that measure wind speed. A cup anemometer, which is simply cups that are spun by the wind and registered. Hot wire anemometer measures a loss of heat from a heated wire, which is then modified and translated into wind speed. Aerovanes, which are propeller-like components that indicate the direction and the vector quantity of acceleration. And sonic anemometers, which are arms that send and receive pulses, high-tech kinds of instruments which are able to evaluate various changes in wind speed. Here's an example of some of the traces of time variations in wind speed and direction for approximately a 6-hour period. So by analyzing these graphs, we can determine wind speed over time. Although the atmosphere is a continuous fluid, for convenience of study, we subdivide atmospheric circulation into discrete weather systems that operate at different spatial and temporal scales. Here are the 4 basic scales that we use. The planetary scale, which is very, very large, deals with weeks to months. An example of that would be trade winds or other winds that we find in large areas of the Earth. Synoptic scales, 1,000 to 3,000 kilometers, days to week. This is something like an Arctic high or a high over California. Mesoscale deals with hours and days, and then we talk about that from 10 to 1,000 kilometers. And this takes place in hours or to a day or so. A severe thunderstorm would be a good example of a mesoscale weather event. In microscale, a meter to 10 kilometers, seconds to hours, for instance, the tornado as a weather event would be considered a microscale atmospheric component. A thing to keep in mind is that each smaller scale weather system is part of and dependent upon the larger scale atmospheric circulation. That is, the various scales of atmospheric motion form a kind of hierarchy. Extreme nocturnal radiational cooling requires a synoptic pattern that favors clear skies, light winds, and calm air, for instance. At a microscale, such weather conditions may lead to formation of frost or radiation fog in a river valley. But regardless of size, all scales of atmospheric circulation are ultimately governed by the boundary conditions of the system.